All right, it's time to talk about graphs of limacons in the polar plane. And these are quite curious little graphs. They have a lot of different little nuances to them, so I will try my best here to explain how these graphs look according to their respective equations. So limacons have equations that look like this. R equals A plus or minus B cosine theta, or R equals A plus or minus sine theta. And the major difference between those two that we see is the cosine and the sine, obviously. And the way to tell the difference between a cosine limason and a sine limason is that the cosine limacons will be situated on the positive or negative x-axis. So, for example, this is an example of a cosine limason with an inner loop. As you can see, that cosine limason is situated on the positive x-axis. Same thing here. This would be a cosine limason. It's situated on the positive x-axis. Same for this one, and same for that example. So all of these are cosine limacons. As a matter of fact, they're all positive or plus b cosine limason. If the b in front of the cosine is positive, then they will be situated on the positive x-axis. But if the b in front of the cosine is negative, then they will flip across the line or the y-axis or the line pi over 2, and they will be situated on the negative x-axis. So for the cosine limacons, if b is positive, they'll be situated on the positive x-axis. If b is negative, they'll be situated on the negative x-axis. Now, sine limacons are not situated on the x-axis. They're situated on the y-axis. So a sine limacon would be up here, or up here, or situated here. If the b in a sine limacon is positive, then the shape will be situated on the positive y-axis. Or if it's negative, it'll be situated on the negative y-axis or along the angle 3 pi over 2. So positive b sine of theta is going to be positive y-axis, and negative b sine of theta is going to be on the negative y-axis. So now that we know how to tell the difference between a cosine limason and a sine limason, let's talk about the different shapes that limacons come in. The first shape that you see here is called a limason with a loop. And you notice that this limason has an inner loop to it right here. These are called limacons with loops. We get a limason with a loop when A is less than B. Or in other words, when our constant here is less than our coefficient there. When A is less than B, we get a limason with a loop. And I'll go into greater detail about exactly what to look for with these shapes in just a minute. The next shape that we might get when we're working with limacons is called a cardioid. A cardioid. Notice that the cardioid is different from the limacon with a loop in that it looks almost exactly the same as the limacon with a loop, except there is no inner circle. There is no inner loop. The cardioid just meets at the pole in a sharp point. And it's called a cardioid because it looks kind of like a heart shape. Now we find, or we can recognize cardioids when A is equal to B. So when A is equal to B, we know that we're going to have the cardioid-shaped limacon. The next situation we might run into is when we have a dimpled limacon. And you notice here that the graph is no longer meeting at a sharp point at the pole like our other two. Now it just kind of dimples in and keeps going. It just creates a little dimple there. Doesn't get the sharp point, doesn't meet at the pole like our other two, like the limacon with the loop and the cardioid did. So this is what's called a dimpled limacon. We run into dimpled limacons when A is between B and 2B. So in other words, when the constant is greater than the coefficient, but less than twice the coefficient. That's when we run into dimpled Limacon situations. And then the last situation we'll have is a convex Limacon. Now notice with the convex Limacon, there's no longer even an indentation on the back side. It's just kind of flattened out on the back side here. There's no indentation or dimple whatsoever. It's just kind of flatter on that side than it is on the other side. And we run into convex Limacons when A is greater than or equal to twice B, or when our constant is greater than or equal to twice the coefficient of cosine or sine. So now let's talk about some things to look for on the graphs of these Limacons, because we can tell a lot about the graph of a Limacon just by looking at its equation. And the first thing I want us to notice is this. 1 plus 2 gives me 1, 2, 3. Next example. 1 plus the coefficient of cosine here is a 1. 1 plus 1 is 2. 1, 2. Over here on the right, 3 plus 2 is 5. 1, 2, 3, 4, 5. Last example, 2 plus coefficient is 1. 2 plus 1 is 3. 1, 2, 3. So if we add the absolute values, now listen to me, it's important that you do not look at the signs of these numbers. Do not look at their signs. Whether they're positive or negative doesn't matter. I want you to take their absolute values. Look at their absolute values. If we add the absolute values of these two numbers together, that will always get us the furthest most point from the pole, or that will get us the point on the big side of that Limacon. The next thing I want us to notice is this. What's the difference in 2 and 1? Well, the difference in those two numbers, they have a difference of 1. Notice that's where the inner loop ends on this equation. They have a difference of 1. So on Limacons with a loop, the difference in the two numbers will always tell us where our inner loop ends. Look at this example, 1 and 1. What's the difference in those two numbers? The difference in those two numbers is 0. Well, that number, 0, is at the pole. And so that number tells us where the point is on the cardioid Limacon. Let's look over here at the dimpled Limacon example. 3 and 2. 3 and 2 have a difference of 1. Again, notice that number 1 tells us where our dimple is. But notice you may look at that and say, well, that's negative 1. Yeah, it is, but it's still 1 unit away from the pole on the opposite side of the big side of that dimpled Limacon, if that makes sense. So 3 and 2 have a difference of 1. Well, that's how far away from the pole my dimple is going to be. And then on this last example, the convex Limacon, 2 and 1, well, those have a difference of 1. And look where my convexness is on my convex Limacon. It's at a unit of 1 distance away from the pole as well. And then the last thing I want us to notice is this. This constant here of 1, look where my graph intercepts the y-axis, if you will. It intercepts it at 1 unit away from the pole on the top side of the graph and the bottom side of the graph. Look here again, 1. My graph intercepts the positive and negative y-axis 1 unit away from the pole. In this example, 3 is the constant that's being added to the 2 cosine theta. Notice where my y-intercepts are. 1, 2, 3 units away above the pole and 1, 2, 3 units away below the pole. And on this last example, 2. My y-intercepts are 2 units above the pole and 2 units below the pole. And that will always be the case. The only difference, all of these examples were cosine examples. The only difference for sine examples is that number won't give us the y-intercept. That number will always give us the x-intercepts, or the distance from the pole on the left side of the graph and on the right side of the graph.